Okay, should we start?
Yeah. So yeah, welcome everyone to this today's lecture on deep learning and microscopy by Udo. So I have worked with Udo before, so it's great pleasure to have him on Imaging ONEWORLD. So Udo did his undergrads from Canada, and then he did his diploma and PhD in Germany from Heidelberg University. And then he went to Greece, and I think then he got a Marie Curie fellowship to work at King's College with Rainer Heinzmann. And he did his PhD with Christoph Kramer, and then he again started working with Professor Kramer. And I think last few years, 7-8 years, he has worked with Christoph Kramer, mostly, let's say, both left-right hand of Christoph Kramer. And now he is a full professor at University of Applied Sciences at Chur. And he does a lot of microscopy hands-on, like microscope development. But now he's more into image processing. And this is something that I also don't know, the deep learning, the new image analysis that Udo has jumped in. So Udo, looking forward to your talk. And we have some great bunch of questions at the end. So yeah, please wait for the Mentimeter quiz also. So Udo, looking forward.
Thank you, Kirti. Thank you everyone for organizing this. It's really a pleasure to be here, part of the series. So I have, about three and a half years ago, I've started as a lecturer in image processing in Chur, and this university is now one of the newest universities, as it has split up with a bunch of other universities. So what I'm going to talk about today is deep learning, and in particular with some hints and applications, deep learning and microscopy. And I'm going to start, of course, with a sort of shallow introduction from machine learning to artificial networks, and what are they really good for? I mean, 10 years ago, very few people have had a chance to work with artificial neural networks for image analysis, and now everyone appears to be doing it. We're going to have a look at advanced neural networks, going deep learning, as that is, of course, what is presently going on. We will find that we need to look at the input data when we go for deep learning, and we're gonna see some applications of this deep learning approach to biomedical image analysis, and in particular then, of course, also to microscopic image analysis. So what is deep learning been used for? Of course, it's coming from computer vision, and if you've had a chance to work and drive an autonomous driving vehicle, then of course you have come across this tremendous progress that we have seen in deep learning for image analysis. So we start that image analysis can be used, well, deep learning can be used for simple I should say they are simple classification tasks. So we can decide what is being presented in an image. And that is something that is not necessarily deep learning, but of course, since the talk is about deep learning, I should also incorporate this. And then later on, we have that we're interested in where the objects are within the images. So we will have a particular region of interest, and we will localize then, of course, what is being presented to the camera. We would have multiple objects typically in an image. And of course, we want to detect all of these objects. We would find their region of interest, or if it's possible, then we're going to be more precise and not only have a proposal region of interest as we are seeing here, but we're going to have something that is sort of pixel based. We're going to assign a certain set of pixels to each of these objects that are being presented. So this is, of course, what we would like to achieve. And before we get there, then we would sort of slowly try and do that. So we're going to use machine learning to do that. And the machine learning approach is, I should say, something that previously has not been called machine learning. I have come across various things that I should rather think they are related to a regression analysis that is most often done, and now everything is called machine learning. So a machine learning approach to image analysis would be something like that. We have an image, possibly of some sort of fungus, possibly something that we would or not would like to eat. So it could be some edible fungus, it could be some poisonous thing, and then we would want to use image analysis to do that. Here we see that our machine learning task would come up with a solution to that, and it would present us with some data, right? It would present us possibly with a classification confidence. Here we have so 69% that this plant is poisonous. That would leave, four people. Hey, you download this app on your smartphone and you go in the woods and you pick one, and then 4 out of 100 people that go into the woods, they would have a problem here. And this is something that is very typical for this deep learning approach. It is a neural network that we're going to use, and a neural network will always come up with an answer. So if you're doing programming yourself, you would very often come across a situation when you have not foreseen what is going to happen, and then your program will simply crash. The machine learning approach is rather different from that approach. The machine learning approach as a neural network, it will always give you an answer, and sometimes the answer is correct, and sometimes it's not, and you have to live with that. So of course, if you do some sort of classifications, and like with a human, and humans do also tend to, every once in a while make an error, then of course that is something that is very common. And still deep learning can help you in doing that. The main goals being then classification, as for instance here with classifying the plants into edible and non-edible poisonous plants, or you could do a prediction. It could do a prediction of where the plant is in the image, if it's left, right, top, bottom. It could, predict some other, like how poisonous the plant is, and others. And then there's some intermediate goals of machine learning. It would have to do characterization, search hypothesis. Can we classify these plants into edible or non-edible plants? Can we cluster them into various forms? The machine learning basics we're going to see here. So what we're going to do is, well, I've come across various books, and they say that machine learning is something that allows computers to do something without explicitly being programmed. And I must say I strongly disagree with this convention, because the computer is not going to do anything unless you operate it properly. Nonetheless, this is sort of a definition that you'd find in textbooks. The machine learning approach is as follows. You have labeled data, and the machine learning algorithm then sort of uses a model. A model is just a system of equations. Can be rather simple system of equations doing additions and multiplications typically. And then you would have in this system of equation, you would have various parameters. They're called weights in the machine learning algorithm approach. Weights, and these could be in this equation, y equals mx plus b. There would be two weights here. We have one m parameter and we have a b parameter. And these weights, once they are fixed, they can be used to predict an outcome y for an unknown data input data x. And of course, the machine learning algorithm cannot do anything by itself. It will not, just by, I don't know, guessing or what, come up with values for a parameter m and b. But we would have to have a framework which allows optimization for this, for determination of these parameters. And then once we have determined the parameters, then we can put everything together, like the system of equation, together with the values that we have extracted from the learning, from the optimization, and have a learned model that we can throw unknown data in, and it will come up with a prediction. So that's the main task, right? That we would have a possibility to evaluate unknown data. First, we put in image data, we train our algorithm, and once we've done that, we can use unknown data and use the trained model, the learned model, to tell us what is being presented in these images. So is there no programming involved? But sure there is. We need to first have an annotated data set, like people would have to come up with a learning data set. What does that mean, annotated data set? We have images and we have corresponding output. So, just a very simple approach here. We have a sensor which consists, let's say, of 1 pixel, just air pressure. We have here values. And we correspond that to what we observe when we look outside. And this very simple approach gives us a possibility to map the input data to the corresponding output. And we can use that either to classify our sensor data. We can classify it at, rainy, cloudy, sunny data, or we can go even further and do a regression analysis. This is the classification result, if you want. And then you can have the regression analysis, and that allows you to see that there is a corresponding correspondence between the observed weather outside and the air pressure. So this is machine learning in a nutshell. For us, with the image analysis task, we're going to have, of course, to have training data set, which is consisting of a lot of images typically. And then we would want to train a model using that training data set. And as I said, the model is going to be probably not too complicated. It's just going to be much more numbers as in this equation. So deep learning doesn't do any fancy math apart from multiplication and additions, but it does a lot of these multiplications and additions. Okay, so what we're seeing here is the concept of this, what is called supervised learning. Supervised learning means that you first have to sit down and annotate your input data. And then once you have done that, you have a corresponding input-output map, then you can use that to train your model. Very often, we're not going to do that from scratch, but we would rather do put in a model and use a model that has been previously trained to do something else. So we have already values for M and B. It's just that these values for M and B, they are good for some sort of regression, but not for the particular task that we're going to use it. And that means that we want to do transfer learning most often. And meanwhile, we have a lot of frameworks where we can do that. So we don't need to initialize the model with the random values, but we would rather initialize it with a model, a trained model that can do something all right. And then we don't need that much of data anymore, but we can also come up with let's say, a reduced training data set to do this transfer learning. And then the artificial neural networks come in handy because they can also do this analysis for us. I said that these artificial neural networks, they're just doing additions and multiplications. And this is going to be a lot of multiplications and additions. So they can consist of many what is called artificial neurons. An artificial neuron is simply an equation. And this equation of multiplications and additions, that is stacked with a ton of other equations of the similar type or a bit of a different type, but more or less the same. And then you can connect one to the other, the output and the inputs, and you get something like that. Okay, here's one equation, here's one equation, here's one equation. You have here your pixels from the input image, and you get sort of an output, a value if you want, for a prediction, where is the object, or you get multiple outputs if you want to do a classification. So here, the pixels of your input image, here's the equations, and here is the output that you get. This is artificial neural networks also in a nutshell. And as I said, the math is not too complicated. Here we're doing sums of weighted input values. So it's not really fancy math. We're going to multiply that with a weight 1, we're going to multiply that with a weight 2, and then we add these weighted values here. And then we can have also, of course, additional layers with multiple input neurons and so on and so forth. So for instance, something like that has been used successfully already in the, I think in the 80s, somewhere around that, has been used a neural network of that size in a very important application. Here we would have, I think, the post office at the time. People would manually select, read the addresses and throw the letters into bins corresponding to the postal codes. And then some smart guys came up with the idea that this could be automated, and you could read the postal code with a camera and use something like a neural network to discriminate between at least the numbers of the postcode. Of course, this worked nicely for postcodes consisting of numbers, and then you would have 10 output values there, and each of the neurons of the output layer that would correspond to one of the digits 0 to 9. And this is, of course, been highly successfully used by post offices all over the world. You would have an input image of a 4, and then your neural network would classify that as a 4. You get, of course, a number of outputs corresponding to the number of classes you put in. In this case, we have 10 classes corresponding to the 10 different digits. And the highest probability in this result is going to be in this bin. And then that means that we would need to assign this image the number 4. And this is rather successful, even with, you should say, this is a low quality image of a 4, but this has been really, really successful, and then has been, of course, transferred to other tasks. So this, let's go back once. This is a simple classification task. And the classification task means that you get one result for the whole input image. And this is, of course, not what we want. We have input images, let's say microscopic input images. We have a number of cells that we would want to analyze, not just one cell which occupies the whole field of view. And that means that we would need to come up with another solution. We would have, in the end, somewhere here in the back, we would have this classification layer. But before we can do the classification of what type of cell is being presented to the camera, we would first need to have a search strategy to look all over the image, find various regions or proposal regions, and then we would analyze all these regions. And in the end, for some proposal region, we would then do the classification and say, okay, right up here is something that is a 4 or a blood cell or a neuron. I don't know. If you do that, like apply that with the very early successfully trained neural networks, you get results like that. You get a number of proposals for each of the possible classes. And for instance, it would say that this should be an espresso maker. I don't know if I want to use that as an espresso maker, but you can do that. And then we have, of course, a ton of different approaches. But in the end, it's not so many different neural networks being used for image classification and analysis. It's just, let's say, maybe 2 handfuls that are really being used. And a lot of other applications and developments of these neural networks is, I should say, it's a bit of on the academic side. They're good, and they are also highly, well, in specific tasks, they are highly useful. But to the broader audience and to the broader people out there, they're not that useful because they are probably really hard to implement in your own problems. And this is where people have put in a lot of effort to make these neural networks approaches being useful. So Of course, one application here in Chur that I have done is face recognition. All the green labels that you see, these are recognized faces, and then there's the red labels. The people that have not been recognized at the time, they were not recognized because they had already left the institute at the time. So the images that are used for analysis were just taken from the web page of the university, and in this group meeting, I could easily spot out all these people. And this is with a simple tool. Probably you can download something similar from the internet and do face recognition and have your own surveillance camera up and running and tell you right away who's going to wait in front of your door. And probably meanwhile you can also buy these sort of devices. So what is the problem that we come across when we deal with these approaches for microscopic image analysis? Well, one problem that I have come across also in computer vision is that it makes a difference how you present your data. So if you have, let's say, a screwdriver and you put it properly with a handle on the bottom and the metal part on the top, it will be recognized. If you have it the other way around, it will not be recognized, and the like. And this is something that is annoying, I should say. These neural networks, they have been developed, using just photographs from the internet, and all the photographs that you would find, they are affected by gravity, right? So the airplanes are always up in the sky, and then you don't see an airplane which is flying, on the back, something like that. And this is of course annoying if you come from biomedical image analysis and you have your, for instance, biomedical cells that grow on covers on the object slide, and then they can be oriented whichever way. They could also be skewed. They could be rotated. They could be tilted out of out of the plane of focus, and that is of course affecting the resolution, the results that we get with advanced neural networks. There's of course mitigation strategies that we can use. We can use, for instance, neural networks that have been specifically designed to have these sort of symmetries incorporated, so that it doesn't matter which way you introduce your image, it can be rotated, tilted, and then you would still get the same result. Or what is more frequently used is data augmentation. So there is a rotation procedure when you train your data. And the automated rotation procedure, this is called something like data augmentation. And the cells that you use for training your image, processing tasks, your deep learning networks, they are rotated automatically in all different directions, so that you don't have this bias when you analyze your images. Of course, this is all problematic, right? Because if your data augmentation is, let's say, too good, you might skip some important results, because during the training you will sort of rotate all your cells and you don't see any gravitational effects after all, which might be there in the original data, but since you have used data augmentation during the training, then you don't see it anymore. Or similar if you use some particular neural networks that have this symmetry involved. Now coming to some applications. Of course, UNet is very prominent when it comes to application for biomedical image segmentation. We can do retinal vessel segmentation. We can do brain tumor segmentation. We can even segment multiple organs in cross sections across the body. Tumor cell nuclei, even whole cells can be segmented, as you see here. We can do skin lesions. We can also have other vessels being analyzed and neurons being analyzed. Using segmentation with deep learning. So this is, let's say, this is a rather advanced use of neural networks, because you don't simply classify the image. You don't search for structures within the image, but you would have, a pixel relationship, which pixels belong to the interesting part. So this is called a segmentation neural network, and the UNet is a prominent approach for that. What is important in this aspect is that it's not only the pixels that are making up these vessels which need to be analyzed, but it's also the surrounding areas. So this is something that people from the deep learning community, they like to call it attention. Possibly a more commonly used name could be context. So you would look at the context of various pixels and see what is around those pixels. Do they connect to other pixels or not? It's been very commonly used in speech analysis when you have a couple of words that are forming a sentence, and you can't just randomly scramble these words. You'd have to have some sort of a pattern. And then you would also see that certain words, they have attention to other words. So green is corresponding to apple, not so much to eating, right? And this is a problem in neural networks, but that has been solved using sort of approaches where you have something that is called an encoder and a decoder. And these are, of course, both networks that are operating jointly. So these generative adversarial networks you would find on any smartphone when you do translate words from or sentences from one language into another. Before, all the approaches were that you should translate word by word, and that has not been very successful. And with these generative adversarial networks, now the translations, they become meaningful and can be really used, because the way the network has been trained is using example sentences from both languages, you should say, and then sort of the one network generates some sentences, the proposal results sentences, and then the other network is going to detect whether these sentences, they could occur in the corresponding target language or not. And this has also been used, of course, in microscopic image analysis. Also there you have a generator, you have a discriminator. So two networks that are, sort of fighting against each other. The generator is proposing predictions, and then the discriminator is going to look at these predictions and hopefully decide that this is a generated result and not the true result. And if you let them run for some time, let's say a long time, then of course both networks, they will always be better and better and better, and the generator will eventually come up with predictions that are possibly as good as the ground truth, or at least so good that we can't distinguish them anymore. Now, another task that is being done is image denoising using deep learning. The question is there, how do we train the model? What can be put in? Before, we use something like an annotated data set. And here, what are we going to use? Is there a ground truth? Possibly we do have images that are not affected by noise, but more likely we don't. We have only noise models. We can, of course, model this noise, additive Gaussian noise, which is mostly stemming from the electronics. We have multiplicative Poisson noise, that is photon shot noise. And then these models we can use on synthetic data, using sort of clean data, adding synthetic noise, and try and feed that into our deep learning network to learn it. The problem there being that the synthetic noise is always not as real as the real noise. So then we would not have a solution to our real data denoising. Or we can have possibly clean reference images where there is virtually no noise. But if we have that, then we have already solved our problem. We don't need denoising then anymore. One possible solution is that we could use blind denoising using a GAN network, which then in itself tries and come up with noise proposals or denoised proposals and look at these denoised images and compare them to clean data and decide whether that is true or false data. And some approaches have now been able to operate even on real image data, like data that has real noise on it. We can use it in microscopy. We can do object detection and classification. This is, something that you can also download and try out for yourself. A task here was to detect red blood cells, white blood cells, platelets. We're using a limited number of training cells with, as you can see, very high reliability. In another approach, we could use deep learning for distortion minimization. In principle, if you have an image toolbox which provides you with, with decent quality images, you could potentially use deep learning approach to improve these images and obtain better quality images. So we could use a smartphone as a camera with a consumer grade camera and feed that into the network and get some results which resemble the benchtop microscope. Right? Meaning that potentially, if your image acquisition device has the potential to perform good, then we can improve the results. Even if there is a cheap optics involved, we can correct the results. If there is a cheap sensor involved, we can correct the results and come up with a high quality image. Of course, most importantly, we can use deep learning also in super resolution microscopy, where we have, for instance, the task of having a map of localizations or having in localization microscopy, having a number of events that we detect in the raw image stack. And we would, of course, try and come up with a super resolution image from that raw data stack. Various approaches have been suggested how that can be done. And we find that deep learning is highly successful in avoiding artifacts. Artifacts are typically occurring when there is a bend, when fluorophores tend to overlap and generate a signal, an overlapping signal, which is assigned the wrong position in the reconstruction. And possibly using deep learning, such artifacts are countered by the deep learning approach, because the deep learning approach knows where the signal should be coming from, or could potentially know where the signal should be coming from. And that means that you can use deep learning also to generate, let's say, or similarly generate from confocal laser scanning microscopy, generate a STET image or a TIRF SIM image or deconvolved image. You can use deep learning to perform these tasks, doing deconvolution. And then, of course, high content screening is another highly important approach where we can analyze lots of data simultaneously and segment that into a ton of different parts of the cell image that has been recorded. Also there, we would have a similar approach as I've shown in the beginning. We would have some sort of convolutional block for the search strategy. We would have in the end a classification layer which allows to have various outputs. In this case, various parts of the cells are possible, and we would get the highest prediction value for hopefully the correct class of organelle that we are presently being presented, or that has been labeled. Again, I should say that these are predictions that the neural network comes up with, and these predictions, you will always have one of these classes having the maximum prediction. It's not necessarily that the class that has the maximum prediction is the class that you would think that is. That's one of the drawbacks of neural networks. You will always get an answer. Even if you put something completely nonsense image in there, like the image of your motorcycle, you would get a prediction there. And then it's up to you what you do with that prediction. Hopefully we will find then some sort of meaningful outcome from such data, and being able to analyze all the cells that are being presented and discriminate in various factors, potentially finding diseases, finding new drugs that are successful and can be used to treat diseases. Of course, you are probably also interested, and then I think this is more or less already the end of the talk, how you could apply that. And there's been tremendous progress in that aspect in the last 2-3 years, that we have now front ends available that we can use to train our deep learning networks without having to go through coding many lines using, for instance, Python or MATLAB or I don't know what. But you could now use these tools simply, from ImageJ or other front ends that people like to use. You can send your data to the cloud and use the cloud as storage, and use also cloud-based services to analyze that data. There's of course free cloud-based services like Google Colab, which has tremendous computation power. You just have to be careful that you don't have the computations running for too long. Potentially you need to after some hours, you need to save your intermediate results and then come back some later time, because after some hours you got kicked out of the Google Colab, of the free service, or you pay for it, and that's of course also possible. Or otherwise you could use, of course, also computer hardware at your lab. The disadvantage there is that you can't simply run it on your laptop, because most laptops are not powerful enough. Potentially, if you have a gaming computer, such a gaming computer could be used for training deep learning networks. You can surely not use any of the single board computers like Raspberry Pi or the like. That's not possible. And then on your local machine, you connect to one of these cloud-based services. You upload your data, for instance, to some Google Drive or the like, and you train your network using the computer power that the provider has available for you, like in terms of graphical processing units. I think Google outperforms many other competitors in that respect. But the disadvantage with Google is that you essentially hand over your data to Google. So if you have an industry project, you can't do that, right? But apart from that, you can then train your network and obtain nice results as are being shown here. So there is a number of literatures have been added to the respective slides, and here's some additional literature if you want to get started with deep learning using Python. Or there's other possible solutions here. Thank you very much for your attention.
Hello.
Hello.
Yeah, thanks, Udo, for the talk. My connection over here is quite unstable. So, yeah, excellent talk. And I guess everyone. So what we do is we do the quiz now, and then we take the questions from the audience. And
right?
So Amanda, can you transfer like so that I can share my screen?
If Udo stops sharing, then I think you should be able to share your screen.
Oh, sorry, yes. Like that?
Something, the connection on my side is not stable for whatever reason. So sorry everyone for the delay.
Should we ask if anyone has any questions while you're just
Yes.
sorting? So I think there was only one comment from, was it Michael, who was saying that there was the warning about most significant warning so far as you don't always get the answer, which was duly noted. But I don't know whether anyone else has any questions. If you do, then turn on your camera or wave your hand and we'll take that.
So, hopefully people can see the screen now and we can start with questions. I think everything is working now. So do you see my screen or?
Yes.
Yes.
Yeah, so this is the warm-up question, everyone. So yeah, after this, we will get started with the quiz. So we usually wait for 10, 15, 20 people to log in. And yeah, so the warm-up question is, since we had the deep learning lecture, so AI is more important than fire or electricity. So what is more important than AI? So we have already some interesting answers. So we see like almost 7 people have logged in. So yeah. The questions are good, and just a reminder that winners will get a fold scope from Royal Society, and it's a very cool microscope to play around at home. So there is something to get. I see 8 people on my screen. So we have Taylor Swift and Britney Spears, which is nice. Some tough competition going on. So Udo, you get to choose the best answer. And whosoever gets our Imaging One World Nobel Prize for the most cheesiest answer. So I don't know which answer you like. Donuts. Donuts is good. So
Donuts is good, but I think empathy is best in my opinion. If we can, survive.
Do we have that?
Yeah, empathy is there. Just below.
Yeah, I see that, and just next to Elon Musk. So it's a nice combination. Coffee, yes. So we have about 19, 20 people. So I think people are logging in now, and so people like empathy, and it has been voted now. Though, so you see it competing with Britney Spears and donuts. So yeah. So Udo, whosoever responded empathy gets Udo's best answer award. So let's start with the quiz, and just waiting for people to enter who might have run away. There are about 10 people. So I think we had 20. So I wait for a couple of more seconds for more people to log in. That's about a good number, 15 people. So we'll have a good competition. So yeah, the faster you answer, the more points you get. So a generative adversarial network. So here are your options. makes use of two neural networks competing with each other, can be used to reconstruct single molecule data, can be used to translate data from one form to another, requires short training times as compared to others. Yeah, that's good. So basically, there are multiple answers which are correct, and so yeah. So even if you get one of those correct of the multiple, you get full points. So that's it. So yeah. The next question. Oh, we also have the leaderboard, which I keep forgetting. So at least I know a few people here, Ian Dobby for sure. So Nemo is the fastest, then SR, Martin, and Ian Dobby. So I think these four guys are in close race. Liz G, I don't know if I recognize, but yeah, at least we have 4 or 5 very close contenders. And let's see the next question. So remember, the faster you answer, the more points also you get. So, and there are multiple answers sometimes can be correct. So deep learning applied to microscopy data can result in a denoised image, can result in restored image, can result in segmented objects, can reduce artifacts and deconstructed images, can induce artifacts and reconstructed images. Now, sometimes quizzes like these, Udo, are super good because everyone gets at least one answer correct. Like it means like no one goes in disappointment. So let's see the leaderboard. We still have the last 4, Nemo, SR, Martin, and Ian Dobby, and Liz G. Actually, Martin has stopped now. So Booyah was fastest in this round. So that's nice. So we at least have like 7 participants almost close, neck to neck. Deep learning network architecture influences recognition of translated objects, recognition of objects rotated in 2D plane, recognition of objects tilted out of plane, recognition of objects with different brightness, recognition of objects with different sizes. Oh, that's nice. So again, all answers were correct. So if you just clicked randomly something super fast, you will get more points. Let's see who is in the race now. So Nemo was fastest in this round and is currently leading. So let's find who is Nemo. So 4th question. Deep learning applied to noisy microscopy data. Performs best when precise noise levels are known, can discriminate between various noise sources. That's interesting. Requires training using uncorrupted data, is affected by model, can induce artifacts in reconstructed images. Yeah, so the interesting option was wrong. I thought like that would be actually a question, if we can somehow, have a network to differentiate noise, that would be the final goal of deep learning, right? So let's go into the leaderboard. So Nemo is still heading, and let's see who was the fastest in this round. So Nemo is the fastest and also heading, so it's a close race again, not much difference between first 3-4 participants. Last question. Training of deep learning networks is best accomplished using targeted computer hardware, high-end GPU, using paid for commercial cloud-based services, using free commercial cloud-based services, any off-shelf laptop. Yes, that would be nice. And yeah, so basically, I think it looks like Nemo has won the race almost. He's leading. Oh, Martin and Liz G are very close. So congrats, Martin. Whosoever you are, if you put your name, we will even clap for you. And if you send us your email address to Royal Society or Stephanie, we will also send you the fold scope. Congrats, Martin. So that's it. Stop sharing my screen. Although we can take questions now if you have questions for Udo. And
So Paola has a question. I don't know whether she wants to turn on her camera and ask it.
Yeah, Paula, go ahead. Paula, a lot of people have questions. So, Paula is still around?
She's just muted.
Yes, hi there. Yeah, I'm not very familiar with the Zoom platform. Apologies. My question was regarding the transfer learning you were talking about. I was curious to know what's the difference in terms of how many images you would need to train an algorithm using transfer learning as opposed to a traditional network.
So if you start from scratch without any prior assumptions, that would mean that you would have to have 10,000s of images, like a lot, annotated data. If you do transfer learning, very simple classification tasks can be done using tens of images, even. Like you can use this GoogleNet or AlexNet and retrain it doing simple classifications, and you'd come up with a solution when you have only 10 images for each of your classes.
How similar does the problem need to be in terms of, for example, for classification?
Doesn't need to be similar. It's just a matter of you'd have to have, objects. When you want to have good results, the objects should be either different, really different, in terms of shape, color, and so on, or you need more data. Right? If the objects become more and more similar, then you would have to have more and more data in order to classify them correctly.
Okay, thanks.
so, Martin, are you still around with your question? Martin Costa. And next, Peter, you are in line with your question. So, Martin, I see you, but I'm not sure if you are still there. Yeah. So, Martin, are you also our winner? I think you're muted. At least I can't hear you. Martin, I can see you and I can see you speak. Peter, you can check the settings as of already.
I was unmuted.
Awesome.
Can you hear me now?
Now it's good. Yeah.
Yeah, sorry. I was unmuted, but using the wrong microphone. Yeah, seems I did win, but I didn't know there was something to win. But
No, you get a fold scope, so congratulations.
What did I win?
It's a fold scope. It's a paper scope from Manu Prakash, and basically it has a pretty good resolution, so you can at least see bacteria and small objects at the level of micron level objects with it. So it's very easy to.
Please give it to somebody who can use. I have a very nice microscope at work, so give it to somebody else and make somebody else happy. Then I'm happy with the honor already. So
okay, that's good.
It was fun playing.
Yeah. So go ahead with your question.
My question was about is there some sort of starting primer? But I already saw a link from Natalie, so I'm going to dig into that.
Okay. Next, Peter, you have a question you want to ask?
Yeah. Is this really because there's lots now about ML and AI? Is this the end of traditional image analysis, or if we want a nuclear one, do we'll just go to black box solutions with an NN and just say these are my images, go for it, or will there be a hybrid kind of machine learning and traditional image analysis for a while? Because sometimes some analysis is quite simple. So is it worth going to ML for most things?
I like this question a lot. You know, makes me think, makes me want to answer depending on where you want to publish, which journal you're targeting. It doesn't necessarily relate to the question, to the problem that you're facing. It is, of course, very important that we still have the classical image analysis, because many problems, they can be solved using classical image analysis. But many people like to have deep learning incorporated in their studies.
So
what we find is that there is a number of guys out there, a number of groups that are developing deep learning pipelines that can automatically be, asked to do different tasks. They've been trained on one problem, and these deep learning pipelines, they can be easily shifted to another task and come up with a solution which is really good and which does not necessarily require the amount of training that we see when we start doing that by hand or with Google Colab. We would spend hours on end training new networks, and if you're sort of having a small pipeline, then that can be done much quicker. And I see also in the area where I'm working now, which is more like sort of industry automation, so there's commercial suppliers which are offering solution, off-the-shelf solution that can be trained rather quickly to do deep learning tasks.
So, Udo, I will ask one last question, which is basically from your question and answer, the quiz questions you posted. So, microscopy, microscope have, like, the noise in the microscope are very characteristic, right? So different noises have very different distributions. So, how can we train these distribution to actually differentiate, microscope various noises from microscope images? Yeah.
Right. Yeah, I remember that Jürgen Hesser from Mannheim University had some solutions to that. He had come up with a classical image analysis tool which can discriminate and tell you how much is the Gaussian noise, how much is the Poisson noise in your images, and you could use that then later on in your denoising strategy. So you have classical image analysis and get the numbers from elsewhere.
So, a very interesting talk, and I think you covered almost all the applications of deep learning, especially for image analysis. So, yeah, so those of you who missed the talk, it will be available on the YouTube channel of Royal Microscopy Society. And that's it. So, Udo, this is also